is an individual member of International Society for Photogrammetry and Remote Sensing. His interest drove him to conduct many workshops and to attend many training sessions. He did a short course on geospatial technologies for coastal and marine disaster and climatic change in collaboration with UNISCAP, Bangkok. GPSRO technology techniques and applications for Earth system studies from SRM University, Chennai. He also did a special course on hyperspectral remote sensing for Earth observations, Dehradun. Also, he attended a special training program on geoinformatics, a summer school on basics of atmospheric sciences, satellite navigation system, open source geospatial tools, etc. He has research experience in various areas like spectral library, handling various instruments like GPS, total station, sun photometer, etc. Also, he's capable of processing satellite imagery, weather balloon experiments, and many more. He has published many papers in journals like Advances in Meteorology, International Letters of Chemistry, International Journal of Innovative Research in Science, Engineering, and Technology. He is a coordinator of ISRO EduSat, Guide for Remote Sensing, and GIS projects, member in College Research Committee, and registered for Global Initiative of Academic Networks. He is currently working as an associate professor in physics at Raghu Engineering College, Visakhapatnam. We are honored to kickstart this FTP and set the tone for a fruitful day ahead. Thank you, sir, for accepting our invitation. You can start the session, sir.
Patrons of the institution, chief patron of the institution. Chief patron of the institution, Sri Lokanathan, Sri L. Naveen Prasad, patrons, Swaminathan, and Dr. Sarvanan, convener of the today's program, Dr. S. Shivagami, coordinators, Dr. Beulah and Dr. Rattan Kumari, and other participants of this second day program, FDP program. A good morning to you all. Warm welcome to you all for this session. In this session, I would like to present. In this session, I would like to present. It's not actually research results, but how basic principles of physics can be used in satellite remote sensing. Is the idea of the presentation is to create students of physics, how principles of physics are playing a vital role in satellite remote sensing. We developed a value-added course also with this theme, role of physics in satellite remote sensing. We are encouraging the college students to pursue this, take this value-added course. In this presentation, I would like to few slides. I would like to dedicate a few slides. What is remote sensing, and then what are the applications of remote sensing, and what are the different. Hello.
Sir, your screen is not shared. Sir, your screen is not shared.
Screen is shared, madam.
Can be seen, sir, here.
Is okay? Hello?
No, sir, not visible.
Your slides are not visible, sir.
Hello? Can I go ahead?
But your slides are not visible. You're audible, but your slides are not visible.
I shared the screen, madam.
இது எடுக்க முடியாதா? Your video.
Now, the screen is now.
No, sir. Your screen is not seen, sir. Your screen is not visible. Yes, sir. Sir, it is visible now. It is visible now, sir.
Is okay?
Yes, sir. Yes, sir. Yes, sir. You
Yeah.
can go ahead. Thank you, sir.
So the presentation will be like this. A few slides I would like to dedicate to what is remote sensing and what are the different applications of remote sensing and how remote sensing can serve different communities like weather and agriculture, forestry. And then few slides, as a title, for the title justification, we will see that what are the different physics principles used in satellite remote sensing. Now, if you see, it's a technology without touching the object, acquiring the information from the Earth surface. It's called remote sensing. The best example of remote sensing is our human eye. You see different objects can be seen with our human eye without, in physical contact. To see any particular object, we require, light has to fall on that particular object and the reflected light should reach our eye retina, then we will get a sensation of vision. Similarly, we require, some source of light. That light has to be illuminated on the object we want to see. And then that reflected light beam will reach the sensors. So the key components are sensor, platform is the satellite, and the target is the, it could be ocean, it could be forest, it could be any earth feature. And it's essential for earth observation, resource management, particularly, when you plan where potential fish is there, if you want to, identify potential fish zone, if you want to, identify where forest is firing, forest fires, if you want to identify, where mineral abundance is more, if you want to see where weather, if you want to give the alarm to any particular area regarding alarm, these satellite data, remote sensing data is very, very important. And, these satellites equipped with sensors, I mentioned the key component is one sensor. They reflected or emitted energy they will take. And weather forecasting, agriculture, disaster management, urban planning are safe. So in earlier days, if you see the remote sensing is with, cameras holding on the hot air balloons, or, they use it to collect the data by holding the cameras by using pigeons, birds, or, by standing at tall buildings, they use it to get the, photographs of particular topographic information. Now see, when we come to direct, how it works, when we come to this one, you can see that some three things one has to remember in mind, that sunlight, it will pass through the atmosphere and it will reach the earth feature. And again, some portion was absorbed, transmitted, and that reflected, and a portion of the light will be, reach to the eye sensor, particularly sensor of the satellite. And, sensors will, once data acquisition takes place with the sensor, and that data can be used for societal application. And if you see, there is energy source and radiation and atmosphere is there, and we have, interaction with the target and recording of the energy, reflected energy by using sensor, and there is a transmission, reception, and processing. And finally, interpretation will take place at a different levels. Particularly, all the ISRO centers are dedicated with, analysis laboratories, interpretation laboratories. Can be used for different societal applications. And there is two types of remote sensing. One is, active and passive remote sensing. Active remote sensing and passive remote sensing. In active remote sensing, like microwaves from radar, lidar, and they use their own electromagnetic waves. They send the electromagnetic waves, and these electromagnetic waves interact with the topographic features, and the written electromagnetic waves, reflected electromagnetic waves, again captured by the radars, and they will be studied. So source and reception will be taken by the radars and in active remote sensing. Whereas when you come to passive remote sensing, it's mostly depends on the natural light, like sun. Sun will emit the energy, and that energy will pass through the atmosphere and reach the Earth surface. And reflected beam in passive remote sensing will be captured by the sensor. By advantage of the active remote sensing is even microwaves, when disaster happens, where there is no sunlight, night time particularly, when sudden things happen where there is no sunlight, sudden disasters happens, like like a landfall, where there is in the absence of sunlight. Now this active remote sensing works well, and this active remote sensing will collect the data without any interruption. And you see in the passive remote sensing, we have sun, and sunlight will hit the Earth topographic features, and again collected back by satellites. Whereas in active remote sensing, if you see, the satellite itself will emit the energy and will collect back the energy. So emission and transmission and receiving, both will be done by the satellite. That is in active remote sensing. You see one beautiful satellite image where you can see the topographic features. And this is, one satellite imagery I would like to show for the purpose of they want to identify where bauxite, mineral is available. And you see that, accumulation of, this sand and silt. They use the satellite data, and they give the, zones also, where accumulation was happened, and thick accumulation was happened, and thin accumulation. These are all, post-disaster studies they have taken. And for future management, they use, these kind of maps. And, different agriculture, different features like mango, citrus, these kinds of things also can be identified. Agriculture features also can be identified using satellite remote sensing. And you see one of the beautiful application, oil spill happens, and that, trajectory of the oil spill, where it is going, and how it is traveling, and what coast it will reach. All these things can be studied with the help of remote sensing. And the crop estimation is one of the best features of this satellite remote sensing. And you see, this is yield, how yield percentage is there. They used this satellite remote sensing maps, and they have seen this kind of maps will help us actually to identify how much food has to be, how much food has to be, imported, and how much food has to be exported, and how many godowns we require for, storing the thing before, Kharif and Rabi seasons. And, here we have, scatterometer data and remote sensing data. It's used for cyclonic thing. And, active fire detection can be done. Okay, what are the active fire locations they did, and carbon pool. These locations also mapped with the help of remote sensing data. So why I want to show all these images is, not only satellite images will help, to identify, to record the images, but also, there are satellites. They won't give images. They collect the data like, water vapor, and they collect the data like a temperature, like the sea surface temperature is a important, parameter in deciding of cyclone, and it collect all the data. And also sometimes there are some sensors, deployed in the space will collect, they collect the temperature, water vapor, all the data they will be collected, even ozone kind of thing, and also different, particularly different pollutants also can be mapped with the remote sensing. Aerosols, that's also mapped with the thing. Pollutants also can be mapped with the thing, with the remote sensing data. So this remote sensing has not only, used for imagery, but also, the data collected in the remote sensing can be used for different societal applications. And particularly disasters, when disasters happens, pre-disaster indication also can be given with the remote sensing data. Like these are the zones where landslide may happen, and even planning, not only planning, but also post-disaster. So what is the what is the financial loss happened, and how to mitigate, and also after a disaster. I know how much is the amount of, in terms of money, how much is the money wastage has happened. Everything can be calculated, and management, particularly for the managing things, pre, post disaster, and also during disaster also, remote sensing data are the data collected from the remote sensing satellites are very, very important. Now we see now in the remote sensing, role of physics. As a physicist, particularly, I always say that not only the thing, not only principles of physics. So everywhere in every process of remote sensing, physics plays a very, very important role, a very key role. Particularly, the very, very basic principles like Kepler's laws, Kepler first law, second law, third law. We see that particularly these laws we learn in graduate physics, but when come to remote sensing, these laws, Kepler's laws, are whatever the physics principles we learned in thermodynamics, optics, electromagnetic spectrum, radiation, energy transfer, all these information, all these principles will play very, very important role. When you see this Kepler's laws, as I mentioned earlier, they will decide. Actually, every satellite has one is a spatial resolution, that how much in each pixel, how much is the Earth area is covered. Spatial resolution, spectral resolution. That means how many bands of information it will give, and temporal resolution, radiometric resolution. All these resolutions are very, very important terms in remote sensing. Particularly when you want to define, temporal resolution. That means the same area of the Earth, after how many days it can be seen. Like suppose satellite is passed over the Chennai today, again it will look the same area, same place when, like after how many days it will revisit the same thing, and after how many days it will revisit the same and collect the same data. These kind of revisit information are the revisit the time and revisit how much area it will see can be decided with the Kepler's laws only. That means the, satellite, which revolve around the Earth is fixed in a different orbit, distance, and, its perigee point, apogee point, everything was, calibrated with the help of those Kepler's simple laws. And now we see one by one what are the different, different physics principles, used in this. So remote sensing uses UV visible infrared microwave wavelengths. And, this whole thing works on the wave theory of the light, electromagnetic wave in the sense, if Z is the direction of, electromagnetic wave travels, propagates, XY direction is the electric vector, magnetic vector will, will orient in all directions. Electric vector, magnetic vector will orient in all directions in particularly XY plane.
Hello.
Hello.
Really?
కాల్ చేస్తున్నాము నేను టీసీ సబ్మిట్ చేయలేదు ఈ కాలేజ్ జాయిన్ అవుతారా లేదంటే వేరే కాల్స్ వేరే
So you can continue.
Particularly infrared, particularly electromagnetic, and the infrared portion of the can be used for thermal imaging and fire detection, and particularly microwave portion of the electromagnetic spectrum used for the soil moisture studies and, particularly in the weather radars. You see what happens, what is happening here. That means what is the importance of physics here. So reflected energy, emitted energy, you might have seen the words over here. So there is a energy source, okay, sun, and the energy is interacted with the atmosphere, then reaches the Earth's surface, then reflected back, again traveling through the atmosphere and reaching the sensor and what exactly important here is, after interacting with the Earth's surface, a reflected beam, and how the light is interacting with the atmosphere. Different components of the atmosphere will, make the light to, by the time it reaches the sensor, lot of things will happen. And now see, reflection, absorption, transmission are very, very important in this one. We have loss of reflection is very important, refraction, because when light travels, it will travel through the different atmosphere layers, and refraction is very important. And when the light hits the Earth's surface, reflection is one phenomena is very important. And different surfaces reflect, absorb energy differently. What is very important here is, how much different features of the Earth will respond to the electromagnetic spectrum differently. For example, water absorbs more infrared, vegetation reflects near infrared. We have to define sensors in such a way that they should see the reflected light. And this is the electromagnetic spectrum. Visible portion we have, and these are shorter wavelengths, and light will shorter wavelength to higher wavelength, it was arranged. And we particularly use this visible portion and some portion of the infrared and microwave portion, and I will show you that atmospheric windows here. You see this one. This is very, very important diagram for the remote sensing. And you see here, these are the windows, And these particular frequencies or wavelengths absorbed by the water and carbon dioxide. And this portion was, and you can use this particular portion, okay? And this particular portion, and there are, these are called windows, frequencies left after absorption by the, atmospheric water vapor and carbon dioxide, different components of the atmosphere. And we can use these particular frequencies or wavelengths, particularly for the, purpose of the remote sensing. And these are called, atmospheric windows. And you see here, we have different spectra I kept here. And what is the, you see, the second one, atmospheric absorption, I have mentioned here. Now, what is the water vapor absorption, carbon dioxide absorption, oxygen, ozone absorption? How much is the absorption of the thing by methane, nitrogen oxide? And how much is the Rayleigh scattering happening? So after absorption by water vapor, carbon dioxide, oxygen, ozone, and everything, methane, nitrogen, remaining whatever the portion left in the electromagnetic spectrum is used for the, so some portion of the UV visible region, and the near infrared, thermal infrared regions. The regions which are left still, the regions are, wavelengths particularly, which left still after the, absorption by water vapor, carbon dioxide, oxygen, ozone, or can be used for the remote sensing. Sensors are so designed to see those particular frequencies or capture those particular frequencies. And interaction of the electromagnetic spectrum with surface features, absorption, transmission. Okay, whenever radiation takes place, absorption into the target, something, transmission also happens. And something was bounced back by the target, and it is redirected towards the sensor. Very important thing is what kind of surface it is. It's a Lambert here. So those things are very, very important. And also, before design a sensor, these spectral reflectance signatures are very, very important in understanding the, in defining the particularly, frequencies operated for the frequencies for which this particular sensor is operated. And you see here the curve of dry bare soil. Okay, what are the wavelengths? It will at what wavelength it will give more reflectance, and the vegetation you can see green color, and water vapor. So if you know these spectral reflectance curves, how much is the sunlight at what particular what wavelength, the reflectance will be high. You can understand. Once you know what are the wavelengths at which reflectance is high, you can you can make a sensor to capture that particular reflectance signature. And you see here there is a small experiment they did to see that how wavelengths will vary particularly. So they have taken a wet soil and 7 days and completely dry soil, and they have collected the how wavelength varies particularly. They have collected these signatures so as to fix the sensor operated frequency. And you see here the signatures, you can see visible region, and how in near infrared region what happens, chlorophyll absorption takes place. And after that, water absorption curves are there. And whatever the remaining thing is there, it has to be seen by the whatever the absorption portions are left. And that means in this one, to collect the soil, weather, water, vegetation signatures. So you might have seen that 0.5, 0.4 to 2.2 is the sensor operating frequency. And we see we give some time to thermodynamics. One is I mentioned I mentioned this electromagnetic spectrum, how they interact with the atmosphere. So this is very, very important. Electromagnetic spectrum study, being a physicist, is very important because what are the portions absorbed, what are the portions, reflected, and because a reflected beam has to be collected by using a sensor. So these curves are very, very important in understanding the remote sensing, in fixing the, sensors to observe these satellite features, these topographic features. And when it comes to this one, thermodynamical, we have, key role, particularly, temperature, particularly temperature monitoring they will do, thermodynamic principles, ecosystems, they can be monitored, volcanoes and everything can be studied using this thermodynamic basic principles. That means based on these thermodynamic principles only, they fix again. Every time our object is only, what is the response of a particular earth feature towards a particular thermodynamic phenomena. So once something happens, how much it is emitted. So why it is emitted, at what wavelength it is emitting. So that our main object is to capture emitted wavelength or reflected wavelength by using the sensor. So to collect this one, we have to see that what is happening and how the earth features will respond to the different thermodynamic things. And particularly very, very important, everything above the 0 Kelvin emits infrared radiation. So this is a basic principle in the understanding of thermodynamics related to remote sensing, and particularly kinetic temperature, and that is related to internal heat, and radiative temperature, that is the emitted energy. And these things very, very important. These terminology is very important in understanding remote sensing, particularly thermal response. And you see here what it will see is it will collect information. Satellite will collect information, but you see different radiance, and the different radiance, different features will give land surface, sea surface. They will give different radiance information. They will give different reflectance based on the energy interacting with the feature. And very important thing is these things, energy conversion, black body radiation, Planck's law. These laws are very, very important to understand energy response to the topographic feature. And what is the reflect, to understand what is the reflected energy, at what wavelength the peak energy is reflected. That means what is the lambda max at which the total reflectance, highest reflectance is taking place to observe with the sensor. So remote sensing generally focuses on the radiative transfer. Radiative transfer in the remote sensing is the electromagnetic, is the process, simple process, how the electromagnetic radiation is interacting with the Earth atmosphere surface and impacting the signals received by the remote sensing instruments. This is what is called simple radiative transfer. That means how much I have given, how much was absorbed, how much was transmitted, why it is transmitted, and at what wavelength it is re-emitting back, and how much energy is emitting back, and how to capture the energy. These are the simple things. And if you see that radiant temperature, how it is affected by different things, there is a kinetic temperature, emissivity is there, solar heating, long wave upwelling, downwave radiation. These are solar elevation, cloud cover. All these things are the different factors impact the radiant temperature, heat capacity, specific heat, thermal diffusion, thermal inertia. So I want to mention that these are the things happening in day-to-day life when sunlight is interacted with the sun. That particular electromagnetic radiation which is emitted by the sun is when it is interacting with the topographic features. And if you see Wein's displacement law, and hotter bodies, peak wavelength of emitted radiation to a shorter wavelength as the temperature of the object increases. So this will give you a idea that if you want to capture that particular radiation of a particular hotter body, then you have to install a particular sensor which can record wavelength, shorter wavelength radiation. That means what kind of radiation you are looking for. If you want to, capture the hotter body, definitely they will emit, after electromagnetic radiation interacting with the hotter body, they will emit, radiation with the shorter wavelength. These shorter wavelengths should be, readily captured by the sensors. And if you see this black body radiation, Planck's law, Stephen Boltzmann law, all these laws will tell you where exactly this peak wavelength, where exactly this peak wavelength is emitted, and what is the amount of the radiation is emitted, and what is the lambda max of that particular emitted radiation. These are all very, very important, observed with the help of Stephen Boltzmann law. And these laws will give you how, at what is the wavelength at which that particular feature, earth feature, topographic feature will, emit the radiation. And, scattering, absorption, reflection, and particularly CO2, H2O, these are the, when same thing happens in the case of, radiation interacts with the atmosphere. Not only topographic features and how much, when they travel through the atmosphere, how much radiation was absorbed, scattered, and how much is the radiation is, what is the wavelength at which this particular radiation is, with what wavelengths are still left to hit the topographic features, and what are the wavelengths at which that reflected energy is reaching the sensor. To understand this one, very, very important thing is Wien's displacement law is very, very important. Stephen Boltzmann law is important. Planck's law is important, and very, very important is black body radiation curves of the particular water and earth surface are very, very important. And they also will take what is the emissivity of they study dry soil, wet soil, water, snow, because what are the wavelengths, particularly what are the frequency region, these particular materials will respond. And surface like water, vegetation have unique emissivity. If you want to do remote sensing of the ocean, they will take care into this one. And good observers are good emitters. They also take this point into consideration. To design particular sensor, this particular emissivity observations they will take. And they also will study different materials, how they respond to the electromagnetic radiation. And you see this image, it will give you different thermal response. Different features are there actually. These different features, how they respond to what are the temperatures. These are all particularly different temperatures are mapped with the help of sensor. And if you see thermal imaging, land surface temperature, heat islands, they will map. And weather forecasting. Weather forecasting requires cloud temperature. When it is called when you speak about cloud temperature, again we have to see that electromagnetic radiation, how it is electromagnetic radiation reflected from the clouds or emitted from the clouds at what wavelength. Because when you temperature, because wavelength is responded with the temperature that we learned with the basic laws of physics like Stephen Boltzmann law, because T to the power of law we learned. So we to see that cloud temperature, to map the cloud temperature and to collect the moisture profiles, this electromagnetic response, electromagnetic radiation, how it is recorded with the sensor is very important. Energy balance, greenhouse effects, all these things can be studied with the basic laws of thermodynamics. And every time when they design particularly sensors, what they do was they will take care of how that particular earth feature, topographic feature is responding with the or interacting with the electromagnetic radiation, and how the temperature of that particular earth feature is impacting the wavelength of the electromagnetic radiation reaching the sensor. Very, very important thing is some people think that even in passive remote sensing, people will think that sun acts as the radiation source, and the radiation which is emitted from the sun is reaching the earth. Not only that, in passive remote sensing, one more thing also happens, that the earth is also acts as a source, because when temperature of the earth increases, it also starts emitting the wavelengths of electromagnetic spectrum. So not only in passive remote sensing we have to consider the sun, but also we have to consider the earth also, the radiations, electromagnetic radiations emitted by the earth. Those radiations also will reach the sensor. And there are different satellite missions are there, MODIS. This is a wonderful satellite, and this will give a different data like soil moisture, it will give air pollutants, it will map, and also temperature it will collect. So MODIS satellite has different sensors of thing, and MODIS satellite is such a designed to collect all this information. It will taken care of all the wavelengths of electromagnetic radiations, and before using this particular MODIS, they use it to use the Sentinel mission, Landsat also, and these particularly Landsat mission data, Sentinel mission data, MODIS data, used for the agriculture purpose and also disaster management studies. And please understand the purpose of this particular presentation is how Wein's law, Stephen Boltzmann law, black body radiation, and particularly Planck's law. These laws which we study in thermodynamics, how they are useful in sensor, in designing a sensor. How these particular laws will help us to understand what kind of at what wavelength, what is the peak wavelength of electromagnetic radiation received by the sensor of a particular satellite. And one more physics principle used in satellite remote sensing is Doppler shift is to measure the motion. And this one, we studied this one. Particularly, I don't want to mess up all these things with the equations, but simply I want to highlight that Doppler effect, how it is used to for remote sensing. The Doppler effect causes a shift in the frequency and reflected from moving objects, which enables estimation of the velocity of the remote sensing images. Particularly synthetic aperture radar in active remote sensing, imagery used to detect and measure the motion of targets like ships and everything. In weather radars, particularly Doppler shift analysis lets meteorologists interpret the movement of the intensity of the storm, clouds and everything. So this is a principle used and a simple shift calculation. So what is new frequency, observed frequency due to the relative motion between the object and the source. And here in this slide, I want to tell you that relative velocity changes frequency of the return signal. Frequency shift is proportional to the radial velocity, which is observed by the satellite. And this particular applications, the particular Doppler principle used in weather radar, as I mentioned, storm, wind speed, everything. And ocean currents, very, very important. Ocean currents can be observed with the help of mapped with the help of satellite remote sensing, land movement. And in airborne radar, velocity mapping can be done. Target tracking also can be done. Particularly if we apply the same remote sensing Doppler principle in LiDAR systems, so is to monitoring the vehicle speed, atmospheric winds, can be done with the help of the Doppler effect in remote sensing. And you see, this is a simple image I showed you how, ongoing signal, return signal is there. So they will calculate what is the frequency shift, and frequency shift they calculate, and they also calculate what is the, objects like raindrops, the scattered signal. They will provide the information, and also size and intensity of the precipitation also they will provide with the help of Doppler radar, Doppler principle. And different optical principles also used in remote sensing, like telescopes, high resolution imaging, Earth observation satellite like Landsat, Cartosat, all these things can be used with different lenses, mirrors. And as I mentioned in the very beginning, Kepler's laws are very important in, including these are the laws actually. And in satellite remote sensing, understanding these laws is very, very important, because position, velocity, timing, and influencing the sensor data acquisition, coverage, temperature revolution, temporal resolution, and to maintain the orbit, optimization of the coverage, constellation, earth monitoring. All these things are just possible with the Kepler's laws. So these are the laws, and how the things are. This is a beautiful image, can be understand with the help of this one. And summary is physics principles are core to satellite remote sensing: emission, interaction with the matter, and detection. Particularly environmental monitoring, agriculture, disaster response are the key areas where this particular physics principles are used. Particularly remote sensing data is used. Particularly, physics principles have big response in this particular area. Thank you. In this particular presentation, so my aim is to illustrate what are the different thermodynamic principles, optical principles, the principles which we read, Doppler effect, the principles like Kepler's laws, and like radiance to reflectance conversion, understanding the reflectance percentage, reaching the sensors. I want to highlight these things. Thank you for bearing. Thank you.
Thank you, sir. Now I request our resource person, organizing committee members, and all the participants to switch on their video for photo session. Participants can share your questions in the chat box, so that after the photo session we can have question answer session. Madhusudan sir,
Yeah.
can you switch on? Can you switch on your video?
Yeah. Madam, you.
We have to put the permission.
Yeah.
Wait a minute, sir. Sir, actually, we gave access to the video, sir. But your image is not visible on the screen. Madhusudan, sir. Actually, from the
Yeah.
beginning, from the beginning, your image is not visible. Maybe your video is closed, it seems, sir.
No. Is okay?
No, sir.
I need a permission from you to, display the video.
Actually, in our list, it is showing that you have access. So both the video and audio
No,
is
no, no.
allowed.
Is okay?
Yes, sir. Now we can see.
Yes, sir. Yes, sir. Yes, sir.
Thank you, sir.
So there are few questions. Can you tell me some input on free software where you can
So
can
now
you
I
hear
request
me?
the participants.
So there are few questions.
Yeah. Madam.
So Earth and planets are rotating in different directions. How the sensors are working during rotation?
Madam, please.
The Earth and planets are rotating in different directions. How the sensors are working during rotation? There was a question posted in the.
Yeah, madam. Sensors are so designed to collect. Actually, madam, there are called sun synchronous orbits, madam. Sun synchronous orbit. So they always sun synchronous orbit.
Okay, synchronous. Okay,
Synchronous orbit. So
okay.
in the very initially they will they design in such a way that they always this particularly satellite will look for sun radiation. Suppose we now we have sunlight here, so satellite will work here. Suppose after 12 hours,
Yes,
we
sir.
will get night, and some other places of the earth will get sunlight, right? So by the time
Yes,
sun
sir.
reaches some other places, even satellite also will go there. You understand? So where
Okay,
it
sir.
always look for electromagnetic radiation to receive from the earth. So it follows in the sun synchronous orbit. They fix the sun synchronous orbits, man. So satellites are deployed in sun synchronous orbits to collect the data. And remaining questions, you can post it in the chat box, madam. I will detail answer all the things.
Okay, sir. Okay, sir.
Detail.
You can also
Even
yes, sir. You can also
Yeah.
answer it in the group
Yeah, yeah.
also, sir.
Yes, madam. Yes,
In the
madam.
FDP group also.
Yeah, yeah,
Okay,
yeah,
sir.
madam.
Thank you so much.
Thank you, madam.
Now I request Dr. Beulah ma'am to handle the question answer session. Ma'am, it is over.
Yes.
Okay. Okay. Now we'll move on to the vote of thanks session. Thank you is the best prayer that anyone could say. To express our thanks and appreciation, I now invite Dr. G. Beulah to deliver the vote of thanks.
Thank you, ma'am. We would like to express our sincere gratitude to all the esteemed participants, organizers who made this faculty development program a grand success. A special thanks to our resource person, Dr. Acharyalu, for gracing this occasion and sharing valuable insights about basic principles, active and passive remote sensing, role of physics and remote sensing, basic laws like reflection, refraction, and Kepler's laws, thermodynamic laws, and key roles of thermodynamics, and how they can help us to design sensors for satellite. So we are indebted to our management, our chairman, vice chairman, director, principal, head of the department, and all for their constant support and motivation. We appreciate the efforts of the organizing committee to work tirelessly behind the scenes to ensure the smooth execution of the program. As we conclude this FDP, we hope that the knowledge and skills gained will be beneficial in your academic and professional pursuits. We look forward to host more such programs in the future. Thank you, Acharyalu sir. Thank you so much. It was very simple I could recollect all the basic laws what we studied in schoolings and in UG courses. Thank you so much, sir. Thank you.
Thank you, ma'am. The feedback link is posted in the chat box. Participants are requested to kindly fill and submit that. And for tomorrow's session, I request the participants to stick on to this schedule because most of us are having holiday on tomorrow. So we are scheduling it from 2:30 to 4 o'clock. So participants can join with us around 2:25 p.m. So please make a note. We need your continuous support on this. With that, we conclude the second day of FDP. We now invite all the participants to gear up for technical sessions ahead. Please refer to the schedule for the sessions and their details. Let's make the most of this opportunity to learn, share, and grow together. Thank you all for your presence and participation.
Participants can leave the meeting now. Thank you.